Hello, everybody. Welcome to this Embeddle webinar. My name is Devdutt Dubashi. I'm the co-founder and chief scientist at Embeddle. And I have with me today my colleague.
My name is Wilhelm Tranheden. I'm a deep learning researcher here at Embeddle.
And today, the topic for our webinar is something really exciting that's happening around the world today, which is from the cloud to the chip, bringing the power of LLMs to edge devices. So that's our topic for today. Welcome to everybody from the West Coast. Good morning to the West Coast in the USA. Good afternoon to the East Coast. Good evening here in Europe, and late night in India and Asia. So let's get started with this webinar, and please make sure to put your questions into the chat at the end. We'll be very happy to have a discussion at the end of our webinar. Very happy to get your questions and start a discussion. So let's get started. So what's the starting point? Well, we know that deploying ChatGPT and all these powerful LLMs is not a very sustainable thing to do in the cloud. So ChatGPT processing at 50 tokens per second, here are some figures that we can find around. It amounts to something like 1 million GPUs, each running at 60 teraflops. This is like 160 companies, each the size of Meta. So these are pretty staggering numbers, and makes it pretty clear in a very stark way that running it this way, AI is not sustainable in the cloud, because the resulting energy consumption and carbon emissions would have staggering environmental consequences. So we need to have the LLMs brought down from the cloud to small edge devices used by people in everyday life, such as on mobile phones. And bringing LLMs from the cloud to the edge has multiple benefits. You could have these benefits shared more widely among all of society, run them on small devices at work or in homes, on everyday mobile devices. You can get smaller latency, better user experience. You can have privacy. You can customize the usage for your requirements. And of course, it reduces the resource footprint on our planet, which is the big sustainability issue for our times. However, bringing LLMs to these edge devices has its challenges. So first, there are challenges because of the limitations of compute and memory capacity in edge devices. So for example, if you look at the memory capacities of small mobile phones, it's roughly of the order of 6 gigabyte. And this has to be shared with the OS and other applications running on the mobile phone. So LLM application should not use more than 10% of this memory, and that means that puts a severe limitation on the size of the LLM you can run on such a mobile device. Another restriction is because of the energy consumption. So here's an estimate saying that if you run an LLM consuming energy of the order of 0.1 joule per token per billion in model parameters, then running a 7 billion parameter LLM will drain the battery within a few hours. A fully charged battery will only be able to sustain this for about 2 hours. So this is a very severe restriction because of the energy consumption of running such large models on mobile devices. A different kind of challenge is because of the heterogeneity of hardware devices. So you have many different hardware platforms becoming available on the market today with many different properties. And the same LLM will have very different performance depending on which hardware device you run it on. So you need to actually tailor the LLM to the particular hardware device that is operating on your device. So that's another challenge. And so the big picture is that we need very crucially to optimize LLMs for different hardware platforms on the edge. Now, we have two recent studies that have come out which set good baselines for those of us who are interested in solving this problem and bringing the LLMs to the edge. So we're going to take a look at these two baselines that came from very strong research groups, the first one at Meta and the second one at NVIDIA. So the first one is from Meta, says the title is Mobile LLM Optimizing Sub-Billion Parameter Language Models for On-Device Use Cases. This was presented at ICML 2024 just recently in July in Vienna, where I was actually present and had a chance to look at that poster. And the second one came out also in July from an NVIDIA group, and it's called Compact Language Models via Pruning and Distillation. So we're going to take a brief look at these two baselines because they offer very useful insights that we can take on board when we, each of us, try and do our own optimization. And finally, we will share some results that we have with our experiments here at Embeddle, our results and experiences. So let's start with the mobile LLM. So this paper starts with the motivation, which is derived from the limitations that you have on small mobile devices like iPhones. And the conclusion is that for LLM models to be deployed on such devices, you need to have them in the sub-billion parameter range, not trillions of parameters like in GPT-4. So you have to go to sub-billion parameters in order to be available on these small mobile edge devices. So we need models that are about, for example, 350 million parameters with 8 bits. So if you use something like that on a mobile phone, then indeed the energy consumption allows the phone to operate for the duration of a day, which contrasts with what we just saw in the previous slide, that if you use the really large billion parameter models, then the battery is drained within a couple of hours. So here, if you use these sub-billion parameter models, then you can continue using that for the whole day, and that's a much more reasonable way to use them. So the Meta group tried to come up with a uniform way of trying to optimize these models down to the sub-billion parameter range, and they use a combination of many different techniques for this. So to use a particular kind of nonlinearity, to use layers which are deep and thin, to use parameter sharing in the embedding layer and in the group query attentions, and also to use parameter sharing again by deploying layer sharing. So they combined a number of different techniques in order to bring the size of these models down into the sub-billion parameter range as depicted in this figure. And we'll just take a very quick look at some of the things that they did in the study. So for example, their study showed that it is much better to use thinner and deeper architectures. So if you have more layers, make it deeper, but have each layer quite thin, that gives you a much better purchase than trying to have wide layers. Then, for example, using group query attention is a very effective way to share weights and so reduce parameters. And so they came up with different experiments on what should be this ratio of sharing the heads to the KV heads divided by the number of, so this ratio between the number of heads and the KV heads. And another very effective way of sharing parameters was by sharing layers. So here one can share the layers in many different ways, as illustrated by the figure on the right. You can have immediate block repetitions. You can have repetition of repeat all over repetitions, or you can have the repeat all over in reverse order. So all of these are potentially if they're all feasible, but which ones are the most effective? So their experiment showed that if you do the reverse all sharing, that is in general better for accuracy, but on the other hand, the immediate block sharing is better for latency because this data is in cache and can be immediately reused. So there are different trade-offs between accuracy and latency that you can get by using different layer sharing schemes. Now we can switch to the NVIDIA paper, where their overall methodology is illustrated in this schematic diagram. So you start with a fully trained LLM, and then the first step, you estimate importance of different parameters, different layers, different heads, etc. So they use a number of different scores to do this. These are scores that have been used in previous studies. So they use a number of such ones to experiment with. And once you have estimated this importance, you can rank the different parameters according to this importance scores. And then based on this ranking, you can trim and you can apply pruning. So whether you use simple magnitude pruning or you do gradient-based pruning and so on, there are many different combinations one can use here. And the final step that they do in this process is a final use of distillation to recover some of the accuracy that may be lost. So this is a final step that is a small amount of fine tuning with distillation that recovers accuracy in the pruned model. One of the starting points they also use is a very lightweight NAS. So the first candidate to use for the smaller model, they employ a very simple lightweight NAS. So not a very full-fledged NAS, but a very simple one where you have the different parameter ranges and the different kinds of modules. And so in this restricted space, they experiment with very limited NAS. Then they use different ways of doing knowledge distillation. So this is a topic we covered in a previous webinar where we saw that there are many different ways of doing the distillation, starting from the classic first proposal, which is to do the distillation on the final logit loss. But you can also do distillation at intermediate layers, as illustrated here. You can do it at the multi-layer perceptron layer, or you can do it at the embedding layer, etc. So there's a number of combinations possible here. Which distillation losses should you include? So we'll see what the recommendation is, because some of them may be necessary in a particular situation, and maybe simpler ways of doing it are okay in a different situation. So here are the overall guidelines that they came up with on the basis of all their experiments, and we can see briefly some of these insights that they have here. So they list 10. We'll look briefly at some of them. So one, I think the perhaps most interesting insight here is that to train a family of LLMs, it's the way to do it is to train the largest one, and then you prune and distill iteratively to smaller LLMs. So this is the most effective way of getting a range of LLMs across the whole spectrum of sizes, and you get the Pareto optimal frontier by doing this. This is the most effective way of doing this, rather than training from scratch at some intermediate size. So this is very good. It's a very a nice uniform strategy that you start right at the outset with the largest LLM and then successively prune and distill as you go to smaller sizes along the Pareto curve. Then another thing they discovered here is that while you might think that iterative ranking of importance and pruning is beneficial in general, but they didn't find that to be the case. So single shot importance estimation was almost as good as doing iterative. So there's really no need to do iterative procedures. Another finding which is consistent with the previous study we saw from Meta is that it's preferable to do width pruning over depth. So depth is good. That gives you benefits. Having width small is better. So deeper and thinner models are better. Then in terms of the distillation, so we just saw that there are many ways of doing the distillation. And so their recommendation here is that using this combination of logit plus intermediate state plus embedding distillation, that is useful and helpful if depth is reduced significantly. Otherwise, if depth is not reduced significantly, it's just as well to go with the simple logit-only distillation loss. I think this makes sense, because if the depth is reduced significantly, you have altered a lot in the architecture, and so it probably helps to do a more elaborate distillation. But if the depth is not reduced significantly, maybe you haven't changed too much. To a simple distillation is just as good. Now, if you want to get a particular model of a certain size, the recommendation is prune a model which is closest to this target size. this also makes sense. This has been seen in previous studies as well. When you do student-teacher model experiments, we see that if you want to get a student, you want the student to be trained, then it's best to take a teacher which is closest to that size, and not otherwise there is a big capacity gap between the teacher and student, and that's not going to work out so well. So when you want to get target size, choose to prune a model which is closest to that size. And finally, lightweight retraining is always useful to stabilize the ranking of several prune candidates. So these are all extremely useful insights, which are things that we can all take on board when we do our experiments, and we can use those as very useful guidelines. So that saves us the effort to try out other experiments which may not be as fruitful. So just a flash of some of the results. So they have results so they applied this to the Nemotron family, which is the NVIDIA family of language models. And they show results here in two categories. One are if you want to go to the 8 billion parameter range, and the other one to smaller 4 billion parameter range. So on these two parameter ranges, they have compared it to others in the same size category, and they show here in these two tables that their models are about the same or better than all the other competing families of similar sizes. So that this strategy that they've done of starting with a very large model and then pruning and applying distillation is very effective. And this is an example of showing that to get a Pareto optimal set of models, this is a very good strategy to adopt. Okay, so now we come to the place where we can talk about our own experiments. So I'm going to hand it over to my colleague Willem to tell us about Embeddle's own results.
Thank you, Devdutt. So really good presentation. And as you can see, there is a lot of public research out there into optimization of LLMs. And there's a lot of opportunity to really tackle these challenges that you outlined at the beginning, which is crucial here for deploying LLMs to the edge. However, a lot of these papers that we talked about today, they actually lack implementations altogether, or they may link to certain GitHub repositories, and they may be difficult to use. And it's essentially one algorithm for one GitHub repository, and it becomes very difficult to combine them. So combining different state-of-the-art algorithms and actually using them for models deployed for real-world application, that can be a real challenge. So to answer this and give some additional insights, we wanted to look into how far can the performance be pushed here on some of these important benchmarks. For example, running the Llama 2 model on Ampere GPUs. And in order to solve this, we would really want to combine multiple state-of-the-art optimization techniques. That is, we want to leverage the best possible kind of structural pruning. And there's a lot of different structures you can prune as well. You mentioned a few today. You can remove whole heads. You can remove channels per head. There's an embedding size that is completely orthogonal. We had this distinction between changing the width of the model versus changing the depth. So we want to apply the best kind of pruning, but we also want to combine this with the best possible quantization. And then there's this additional cliff to get over, and that is that we actually want to optimize this for any kind of target hardware. So all these models that people are building, they need to go out on a wide range of very diverse hardware platforms. So to give you some insights of the performance you can get if you really squeeze out the best of the state of the art, here we see a graph that illustrates on the y-axis the accuracy of various versions of Llama 2 and derivatives of Llama 2. And on the x-axis, we see the seconds per token. This is how many words would be, or close enough, how many words would be produced by the language model per second. And, or sorry, the opposite, the seconds per token. So you want to be as far as possible to the left here. So a very fast model will have very few time spent per token. And what we can see is that the vanilla Llama 2 models, that is Llama 13B and 7B, directly from Facebook, but still run with proper deployment techniques like at least the BF float 16 quantization, etc. They obviously have a trade-off here, that the Llama 13 is bigger and slower, and the Llama 7 is slightly worse in accuracy but faster. These are the blue points. Then we see some of these public papers here. Some of them very recent, like that said from CVPR of just last year. So, for example, this the unreasonable ineffectiveness of deeper layers here in purple. This red here from very interesting paper from Nota AI, and then this green one here from LLM Pruner, where we see that there's a clear loss here in accuracy. Like, you can make the models faster, but it's actually very difficult to maintain the accuracy, especially when you evaluate them on the target hardware. So in order to solve this, you want to have a very good combination of techniques like pruning and quantization. And if you do this, you can actually start from something that looks closer to the 13 billion parameter model, but you could compress that to a level where it's actually significantly faster than the 7B. And that is what we did here for this model highlighted in teal. It's a model that is a derivative of the 13 billion model, but it's been compressed to such an extent that it's even much faster than the 7 billion one. And we can see that even though it's a compressed version of the 13B, it still has much higher accuracy than the 7B. So it's really all about finding this best combination of optimization algorithms and applying it to, in this case, the Llama 2 model. So we also have some very interesting results coming up. You may reasonably have the question, well, here we demonstrate the combination of pruning and quantization, but in the previous slide, we also mentioned neural architecture research. And we also saw some very interesting results on knowledge distillation that Devdat pointed out. So this is ongoing experimentation from our side, and we're definitely looking forward to showing you more of this nature in the future. So with that, I think we have some conclusions we would like to make. And that is, in order to reap the full benefits of large language models, you need model optimization. So in summary, enterprises, they are rushing to use these LLMs in different applications. And like Devdat pointed out, the energy and resource demands of running these models are mind-boggling. And both in terms of that the energy and resource demands are high, but there's also just an inherent difficulty in getting these to run at the edge. There's a lot of benefits to the edge, resource, but also privacy, etc. And in order to achieve this, you really need to optimize these AI algorithms. And and this point, hopefully, we can talk a lot more about in a follow-up webinar. And that is, how does this actually work when you go to a wider variety of edge devices? We presented some NVIDIA results today, but our SDK, it supports a wide variety of hardware platforms. So we're of course looking forward to showing you more on other hardware platforms as well in the future. And I think with that, we would very much like to wrap up. Thank you very much for listening today, and please stick around, because if you have any questions, we will open up the chat for a Q&A discussion now. So if you have any questions, yes, please let us know in the chat. And if you have other questions, then definitely feel free to reach out to us directly with our contact details here. But with that, I think there already is something posted here in the Q&A channel. The question is, running on LLMs on different edge devices hardware will have varied performance. How would you balance quality and speed if you want to provide a good user experience? Yeah, what's your take on that, Devdat?
That's well, should we call it the $1 million question?
Yeah.
So I think that's the absolute key, right? So we are going the fact that there are so many different hardware platforms makes this problem extremely challenging. It's not going to be a simple one size fit all to it. So the results we showed you today, as William said, they were for NVIDIA, and now we need to do more experiments and see that these optimizations will be tailored to very different hardware. So the way we do it here at Embeddle is we do take various measurements from hardware devices into account when we're doing the optimization. So this is very crucial. We need to take different ways of describing the hardware, measurements that you can make from hardware, and so on, and put that into the loop of the optimization. That's absolutely key. So that's why we call our whole philosophy of optimization hardware-aware optimization. That's always going to be important.
Yeah, I think I couldn't have said it better. And there's another question here: if the recording will be shared. And yes, we do. We have recorded this session, and we will be sharing it. We will be sharing it soon.
Absolutely. So keep looking at our website, and we are going to put all this stuff there, so you'll have access to it. And if you're interested in discussing something that you find there, and you come back, we are very happy to continue the discussion in a follow-up discussion somewhere.
Yeah. Another question here: if to what extent does these algorithms translate to vision transformers?
That's a very good question, right? So this is indeed, we see many interesting differences between vision and language models, transformers. So even though the underlying architecture is the same transformer, but there are very notable differences in when you try to optimize them. And somehow it seems that, for example, the language transformers, they seem to be much more amenable to optimization than vision transformers are. And why is that the case? Well, that's very speculative, right? But Willem has some theories about that.
Yeah, and I think to give some nuance to what Devdat explains is that for language models, it seems like you can do a lot of compression to the model, and with very minimal fine-tuning of the model, you can still maintain a lot of the performance. You can optimize vision transformers to a similar extent, but what you usually find is that you do need to retrain the model in a lot of ways. As for why this is, I think it's a very case to case, like the specific optimization techniques, case to case. But if we take knowledge distillation as an example, it actually originated for vision in the old days with Jeff Hinton, I think in the 90s, was the seminal paper on knowledge distillation. That was something that was originally designed for vision. And there was this idea that a large model, when it makes a prediction for a certain image, it will not just predict the class that is, the ground truth, but it will have some additional information in the logic of the other predictions. For example, if you have an image of a dog, maybe there's a field of grass and a share in the background. So there's a little bit of share in that image, and that is useful information. And the large model, it will have predicted, hopefully, that it's a dog, but it will still have some share there in the prediction. And transferring this information to the smaller model, that should improve the smaller model, and it does. Of course, this was classification specific. There's others for other vision techniques, etc. But what the community found is that these are even more applicable for transformer models, for language models. And I think that's a very clear, to me, a very clear conceptual case for why that is, because when you do image classification, maybe you have 1,000 different classes. You may have this situation with a cat and a dog and a share in the background. But for language, if you're predicting the next word in a sentence, it truly is a distribution of words. Like there's no singular ground truth here that it was in the previous example, where the main object of this image is a dog, and there's some share in there. When you're predicting the next word in a sentence, there's so much richness in that distribution, and that is what we're trying to model with language. What is the probability over the set of words? And when we train it, we will of course give it one single word, but what it actually learns is the distribution. That's what we're actually learning. So transferring this knowledge to a smaller language model, I definitely see why that is, so to speak. The theory matches the practice here.
Yeah, so it's a very interesting observation here that the probability distribution of language models is very different from the distribution of vision models, and that might be why you see the very different qualitative behavior in these two types of domains. So language versus vision, very different tasks, and that reflects in the different performance and properties of these models.
Definitely. If you are interested in vision transformers, we do have we even have a separate webinar actually on vision transformers. Actually, I think the title was "Are Vision Transformers Ready to Take Over Edge AI?" So if you want to learn more about vision transformers, then check that out for sure.
So maybe I can just throw in a question here, which is that when you showed those results from Embeddle, you saw, first of all, that you were able to take the 13 billion way over to much smaller than the 7 billion and still have much better accuracy. And also, you were way better in accuracy compared to these other models that you got from papers, the Nota and the LLM Pruner, which are well-known papers in this area. So what's the secret sauce? Why do you think that you ended up so much better than either of these two?
It's an excellent question, and I want to highlight that, for example, the LLM Pruner, it is a very good paper, and they have a good GitHub repository as well. But they only do one specific thing here, and that is in the LLM Pruner case, they prune certain kinds of structures in the model, and the paper and also the implementation does not really yield itself to combine it with other kinds of techniques. So we do a superset of what the LLM Pruner does, but it's an excellent paper, and we do incorporate those kinds of structures. The secret sauce, of course, is maybe not completely revealed here, but an essential component is definitely just having the combination of these optimization strategies. That is, you don't only prune these specific structures. You combine it with other things like very low bit quantization and that kind of thing.
Yeah, so I think that's a very important message that is consistent across all of these applications, that you need to combine several different techniques. There's no one-shot approach to it. There's no one silver bullet. You need to combine many different techniques. And that's one of our, I think we would like to say that's one of our strengths here at Embedded. We actually exactly do this. We combine the best of several different techniques in order to do our optimizations.
Here's another one. Has there been any test running LLMs on Qualcomm devices? And I think this is an excellent question, because we're actually working on something very similar to this right now. So we would definitely want to follow up. So if you do have, if you do want to talk about this more, we should definitely have a chat.
Now somebody asks about, well, what about the next series of Llama models? Llama 3, Llama 4, what's going to happen?
That's really, really great. We are very, very eager for the Llama 4 release. And I can assure you that as soon as the Llama 4 release hits, we will make something.
So hold on.
That's a guarantee.
Hold on to your seats and come back for exciting stuff from Llama results on Llama 4. Okay, maybe that's a good place to wrap up for this time. So we're set the stage here to see exciting results on when Llama 4 is released, and we'll see you again then, if not earlier. So please keep coming back to our webinars and asking your questions, and we'll be very happy to take up a discussion on these kinds of topics. So let's keep in touch. Bye.
Bye-bye.